Well, before we start, introduce Kevin, that will be the course helper today. And the idea today is like have a brief review of yesterday afternoon, what we have done with the shared memory, constant memory, and streams. And if we have time, maybe we can explain the. Oh no, this is day 2. We are in day 3. We can explain how we can create a graph on heap. After lunch, we will have a management of memory using more than one GPU, and also we will introduce the last exercise of the conjugate gradient method, the CG method. So regarding yesterday, we are have a shared memory. Okay, now it works. Also, I added some more text to the lesson, so you can have a look. And yeah, I'm explaining a little bit more the common use cases of the shared memory, benefits, characteristics, etc. Also explaining a little bit more about the branch divergence that I mentioned yesterday. So the exercise also I upload the solution of the exercises here. If you go to the solution folder, you can find the exercise. I will try to make this a bit bigger. So what? Well, first of all, the exercise is the following is implement the vector scalar product of so the function d dot. So it's the multiplication of the elements of x with the elements of y, and the total of the addition of all of these elements. So if we go to the solution, here I kept d dot serial, that this is the what is included in the template, and this is like one of the. I will try to make this. Yeah, this is the. So this is one solution. I guess that for this exercise could be more than one solution, but well, this is like a one that. So for this one, we use a temporary array that is in shared memory. Said temporary because it will be this array will be available during the duration of the kernel. Once that the kernel finished, the array is gone. And the trick here is, as you remember, shared memory is only inside the memory is available inside a block. So we need to make the size of the temporary array would be threads per block. So we will have one position of one double per thread. So that's why when we index this array, we use the thread index. We don't use this combination of thread ID. That is a combination of block ID, block dimension, and thread ID. And we initialize to 0 mainly because when we do here the for loop, we consider the elements that are the multiplication, but also we may consider the elements that doesn't meet this condition. So in order not to add numbers that are not or values that are not initialized, that's why each thread initialize their position in the temporary array with the 0. So we have this. Also, we do a synchronization of our threads in order to, once that all of the threads reach this synchronization, we are sure that when we do the for loop, this array has been updated. All threads have updated the array. What else? Well, the update is done in parallel, and when for each only one thread per block, do the actual the addition, the sum, and do the atomic addition. In this way, we rather than doing a lot of atomic additions, do only one. The second part of the exercise is to do the same operation, but only using atomic. So it's pretty simple. So we use this. So for each every time that we want to update, to add the multiplication of x and y to result, we use an atomic. What is the problem of that? That this will create a lot of contingent, because will serialize the code and will create a lot of overhead, because result will be updated in serial, like one thread update the result, then another thread update the result. And if also if we do this with atomic operations, you need to log the variable, update the variable, read the variable, update the variable, and then unlock the variable. So if I delete the profile, but I think also this kernel was taking, only this kernel was taking 2 seconds, while the rest of kernels, they were taking, we'll say, thousands of nanoseconds, but was not as long as 2 seconds. I see there is a question in the chat. Yeah, there is the question of the if. That's a good question. But cost. It would be worse if you see here what I could have done. Okay, I will switch the window. So exercise. So talking about the if that will cause another option that I could have done is like add here else, and then the tmp thread idx.x equals 0. And then this line I could comment that line. But for instance, creating this, this will create divergence between both, because also you need to think about that as like a vector, or like a vector operation. So will be like two blocks. So one block that does this, and the next block that does this. But because we don't have a, let's see, this, there will be a block that does this, and another block that will be idle. So not sure if that makes sense. So yeah, here is let's say that a thread either does something or not. So what we are trying to avoid is like different threads that do different things. If some of them are idle, fine. Like for instance here that only the thread 0 of the block does some work. Yeah, it's sometimes it's impossible to avoid some when we do some reductions or some operations. Yeah, but I mean the idea is to minimize the number of them. So well, this is like one of the exercises. The second one is about where we were talking yesterday. Okay, we'll switch again. I don't know. Yeah, I'll switch. Share memory. Also in constant memory, I updated the lesson, added some characteristics, benefits, use cases, etc. And actually, we have this exercise that I noticed the solution was actually was written by one of the course developers, and that solution doesn't use constant memory. It's like a kind of a follow-up of previous exercises. So it was a combination of the multiplication of two vectors and the use of a constant alpha. So it's yeah, the matrix vector product. So the solution is here as well. We'll make this a bit bigger. And also using the solution is there are different, we have a different kernels in case that you want to play with the performance and see which one works best. So I think the original one that is including the, is my kernel 0. I thought that I'm all the time using the pointer of my, I see that it's not on the is not a share. Yeah, just only this. Oh, I see that in the chat, sorry, there is some questions about the previous exercise. Well, I will briefly explain this one, and we can go back to the. So, I mean, what I want to explain of this one is that is similar to the previous one that we have seen, and in the exercise there are several steps. So we have each kernel. So we have a make kernel 0 for the, let's say, the original kernel. So after the step 1, we have this kernel that, if you see, is similar. Is we allocate some temporary shared memory, because the variable is temp. Shared memory. We use that memory. We synchronize threads, and then we do the thread 0 in each block. Accumulates the values and do the atomic operation. Here is not possible to avoid. I see that there are some comments that maybe we can see that in the previous, using the previous exercise, because what you are doing with the how to explain. So what we are calculating some results per block, and we save these results on shared memory. Once that we have all of these calculations, what we do is we go through all of these numbers, all of these values, and we create this atomic adder in order to get the summatory of all of them. Sorry, this. Well, here also I have another kernel implementing step 2. That is, is like a bit more complex, because we use a two-dimensional array on shared memory. And also here in step 3, we fix in order to make the iterations coalescence. But yeah, the solution is here. So and also we have all of these different kernels, so you can play with them and execute them. I would like to come back to the previous section, because I see that there were some questions on the chat. Is this we'll try to make this a bit. So this is the solution of the previous one. Is because I see that there are some questions in the chat. Is clear how this has been? I'm showing this that rather than the 2.6, because that one is a bit more complex, but this one is, let's see, easier to understand. Okay, so since that is more or less clear, Anyway, well, we will have plenty of time today for the exercises, so that's an interesting question. I should have a maybe I can. So the answer to that question is yes. So if you want, we can do it quickly, and you see the results. I can do that. Give me a. Okay, we'll share my own screen. Sorry. Oops. So well, actually, I can do it in a. Yeah. One moment, this exercise. So what we will do is we will execute I think it should work. I need to. So what I will do is I will execute the 3 kernels and see how much and profile them. Load the modules. Need to make, and then see if yeah, this is okay. So it will take a few seconds. Yeah, this is done. So if I do result that. So yeah, you see the difference here. I will I will copy that in the chat in order to so the atomic one takes almost 2 seconds. The serial one takes 11 million nanoseconds. And if we do the parallel one, that is like a more optimized one, takes like 100,000 nanoseconds. So I can copy also the numbers here. Maybe we can edit it. Just to make this clear, the numbers. Oops. Seconds. Oops. So this is the performance difference of using atomic serial, that is the one that is, let's see, a kernel that is not optimized, and a more optimized kernel. The problem with the atomic one is that I don't remember now how many positions of memory. I think it's like a 1000, or I can check quickly. The problem is, imagine that for each position of the vector, you need to do a lock. That this is a very expensive operation, lock a variable. Then you need to read the value of the variable, do the operation, update, and then unlock. So all of these locks and unlocks will take ages to do them, and that serialize the code. Actually, this is a common problem when you parallelize some code. If you do a lot of synchronization points, or to lock a variable that is constantly updated, the performance gets damaged, and is quite expensive. So well, here is the clear example that it's pretty simple. The kernel is just adding an atomic addition, but yeah, it's see, there is a comment that yeah, would be. I'm pretty sure that if we compare with the HIP Plus will be more performant, because the that library is yes, well optimized, and also they use a lot of tricks to improve the cache of the locality or memory access. So yeah, well, this is the theory. Maybe maybe our kernel is the better, but yeah, I doubt so. But well, yeah, that actually that would be like an interesting exercise. I will save this. Oops. Let's see if I remember how to use like that. Oh yeah, okay. Oops. Yeah. Right. So this is regarding this exercise, and we are in the other exercise is about streams. That I think I have here the solution. So this exercise was simple, was modifying the code in order to because we do two copies from memory to from memory? No, I was from host to device. We do two copies. So the idea is to create two streams, and in the stream one does in parallel one of the transfers, and the other stream does the other transfer. So what we do here is we create the streams with this. I will guess it's big enough. But heap stream create. Also, we define these two variables, that is stream 1 and stream 2, that are here. Yeah, here. So the modifications are, yeah, we create the streams. Well, also another part of the exercise was to use ping or locked memory with the heap host malloc. So rather than using a new or malloc, we use heap host malloc. Same for well, x and y. We initialize x and y. And here is where we do the transfer. Sorry, the transfer is done here in parallel. So here what we do is we copy x and y from from host to the device. Also, one trick that I use in order to remember the order of because you see that is dx, so first goes in this case the device and then the host. So a trick that I use normally is that dx, so this is the equivalent of doing this. So if you see in this initialization, the order is the same that this one. So in that case, I never forget what is the order, what is the source, destination, etc. Also, well, here is important to the kind that is hosted device. But yeah, always remember that when you use memcopy, memset, etc., this is like a trick that I always use to. So I execute this, that this is like an asynchronous way. Then we do all of these operations and then we synchronize. There is a comment in the chat that actually the comment is fair because we do asynchronous memory copy and well, these operations are pretty fast to do, and then we do the synchronize. We need to do this synchronization before the kernel because the memory, let's say, needs to be transferred from device to host. Sorry, again, from host to device in order to launch the kernel. The idea here is here you can do other operations while this memory is transferred. So maybe it doesn't, in this case, we don't get that, let's say, performance improvement to doing this like in a parallel. But imagine that while the memory is transferred here, you are reading a file or you are doing something else. So in that case, you will get more benefits. There is another question in the chat that you could get like more performance if you combine you have several streams, you combine a memory copy or memory copy with a kernel execution. In that case, you might get like a better performance. Or also with the this example is as Kevin said, is like a quite simple, so you don't see that much performance. But could be other cases that the memory transfer is like a way more heavy, or could be the case that you can get good performance. Also, I added in the documentation, I added other examples though where the streams could be useful. Just to finish that, once that the kernel is finished, we need to destroy both streams and free the memory that the ping or locked memory that we have created. There is a question in the chat, like the question is if we do a mem copy, an asynchronous mem copy in stream one, then we synchronize stream one, and the first option is like I would say the same as doing a synchronous copy. The thing is when we use streams, I think we need to use asynchronous, but the first option that you are commenting is a blocking mem copy, I would say, and the other one will be no, I think the first one, to be honest, I would say that are similar performance. I mean, you can see a better performance if you are transferring a lot of memory, or I mean, it's not clear. So synchronize doesn't only synchronize string one, doesn't only stop string one. It does. That's a good. I will say, maybe I'm wrong. I will say that this operation is blocking. Actually, the best way to check in the
Juan, so this is quite an important point, so I thought I'd chip in here.
Yeah, please.
So it is important to realize the HIP stream synchronize does block on the host. So this is the whole point. So at this point, by issuing HIP stream synchronize, we can be sure that the actions submitted to the stream are complete.
Yeah.
So
yeah, thanks. No, go ahead. Yeah, it was. I was just checking the. Sometimes when we have like some maybe it's not clear when we check the documentation, it appears what you said that is blocking is this one. Let's see if that loads.
So the idea of this is to try and expose parallelism. In this particular example, it may not make a huge amount of difference. But for example, if stream 1 was sending data to one location and stream 2 was sending data to another location, these may be able to occur in parallel.
Yeah, and just to is what is a host synchronous. So the host will block until the specified stream is empty. So there's another question. So the string can be pinned to host.
Do you mean host threads here? Do you mean host? Yes, I think there is some behavior associated with, you can, in principle, associate streams to actions on host threads, but that's getting a bit beyond where we're at the moment.
Also, maybe this could be solved with the graphs, like having, later we will see graphs that is like a kind of similar. It's another way of implementing dependencies or between kernels and memory transfers. So maybe the answer could be using a graph, or but we can revisit that later. But yeah, some point you will the problem at some point before launching the kernel, you need to do a synchronization point because the memory transfer should be done before we launch the kernel. So that's the. But what I mean is these questions are interesting to answer them and clarify them. Any other questions before we go for a 15-minute break? If not, let's have a quick break until 11. I will share. Yeah, you see mine. So yeah, let's do a online break and we'll be back at 11. Actually, that would be a good continuation because we will explain the graph API and see how we can handle all of these dependencies with a graph. Okay, so before, welcome back. First, before explaining the graphs, what we'll do is we'll see this exercise with the profiling tool with the Perfecto and see. Actually, I need share this tab. So this is the whole profile, and also there is something that I'm not sure if this is like a big, I'm not sure big enough or not, but you see that well, like the whole profile heap stream create takes a lot of time. So I didn't have time yesterday to measure the work time of the different solutions, but also could be the case that we try to improve some a piece of code, and we think that in theory it will be faster, but then when we run that in theory improvement, it will take more time. So it's always like a good practice that every time that you improve the code or you think that you are improving the code, compare both the solution, that the solution is correct, and also compare the performance. Because you may think that you are doing an improvement in performance, and actually could be the case that you're still the way around. It takes more time, or okay, maybe it's more performant, but the solution is wrong. It's not the same. So these are two things that are very important every time that you do a code modification. Check performance and check that the solution that the code provides is still valid. Anyway, I see that here we have like most of the time is a heap string create. I'm not sure if you see here is where the copy host to device is done. I will try to zoom in. I think how I did, yeah. I think I need to. So yeah. So you see that in theory, rather than done in parallel, are done one stream do the copy host to device, another stream do the copy host to device, but they do in like in a different times. So for instance, in these cases, you don't see that much. Well, you see that the copy host to device is done at the same time in parallel that heap mem set. Actually, yeah, I see that the sample is tiny because yeah, the copy takes like way less than the heap set. I think yeah, this is the call heap mem copy asynchronous. The other call. Yeah, I'm curious. Yeah. So in theory, these are the two copies, but yeah, not heap mem set. I'm trying to move to the other, but maybe I would reduce the. Also, if I zoom here, this is the heap stream, the synchronize, the other synchronize, and then I launch the kernel. Then I do the other MIMP, the copy from device to host. It is done here. Where the destroy of the streams. So yeah, here we can see the. Okay, so yeah, this is the. Not sure if there are any questions. But yeah, these exercises are like a small. You want to like maybe have a. You can increase the size of the vector or do some other operations, and maybe you can see more information here in this in Perfecto. Also, there is other tools that we are not covering. That is Omni. I think it's called OmniTrace. That can give you a bit more complex to use, but they can provide more information. Okay, so I will switch. So it was a question before that actually was interesting about we were talking about the dependencies, how we can model the dependencies in case that for some reason we need to copy several chunks of memory, and one kernel depends on one chunk of memory, the other kernel depends on other one, etc. So to solve that issue or to improve, let's see, maybe the logic of when we have several kernels to handle better dependencies and also improve performance, occupation, etc. We have the idea of graphs. So a graph is you need to think that each the node of the graph could be is a chunk of work that could be a memory transfer or could be a kernel. And the edges of that connect the nodes are the dependencies. So what we are doing so far, thinking, well, if you see this graph ABC, so we have the graph, so let's say A could be a memory transfer, memory copy from a host to device, B could be a kernel, C could be the copy from a device to host, well, we finish the execution. But also could be the case that, yeah, you do a memory copy here with a memory transfer in A from a host to device, and B and C are two different kernels that do two different operations. Well, the end, yeah, it's not. So this is the idea of also this type of graph is a directed acyclic graph. So it's a type of graph that is they have like a beginning and an end. Some sort of direction. So the important part of this lesson is to understand the concept of a graph. So again, each node is a task that could be a memory transfer or kernel, and the edges that connect the nodes are the dependencies. So for instance, if again, if we are copying several parts of memory, maybe one kernel is dependent of one copy, while another kernel could be dependent of another copy. So in that case, we can model better dependencies and keep organize the nodes of the. So these are regarding the answering the question. These are two examples. We can have a more complex. Well, here we have only three nodes, but we can have 5, 10, and we can have others. So this could be way more complex. So we can have more nodes, more dependencies. So yeah, this is only two examples. So to create a graph, well, this is the definition here, and we use heap graph create that we use the variable that we have defined before, and we use well, for the flags we use 0. So model will be something like that: define the graph, the variable, create the graph, do all of the work, and then destroy the graph. If you remember, we have something similar with the stream. Define the stream, create, and destroy. So here is similar, but with the graph. So yeah, there is answering the question in the chat exactly. You can model the graph as you want. You can have several dependencies, several nodes, and that would be possible. In this case, B is dependent on A, C is also dependent on A, and if we have rather than N, if we have another task called D will be dependent on B and C. So the thing is, the implementation is a bit more, let's say, difficult than using a stream, because we need to add all the nodes and dependencies to the graph before launching the graph with the heap graph launch. So we will see that we have two. Well, actually, there are four node types. So we have a mem copy operation, heap mem set operation. We also have a kernel node and a CPU function call node. So if we define a kernel node, so imagine that you have this function that is my kernel. We will need to set up all of these, well, the pointer to the kernel function, the kernel arguments, and well, as before, the dimension of the grid and the block, so the number of blocks and the threads per block. Once that we have all of these, we need to set up the parameters. So set a function, the kernel parameters that are the arguments that goes to the kernel arguments, blocks and threads per block. And once that we have that, we add the kernel node to the graph. So it's we need to create the graph, and then we need to create the nodes that are in that graph. That in this case, for instance, we are creating a kernel node. To create a kernel node, we need to specify the kernel that the node will call, parameters, blocks, threads per block, etc. And similar with the mem copy node. So for the mem copy node, we need to have the source pointer position that we want to copy, the destination, also the extent, so the size, and the kind, so the direction of the copy, if we are copying from host to memory or the way around. So for instance, if we use this, if we want to convert this operation to a node, this operation is copying from host to device and data size of a double, host to device. We will need to define something like that. We need to define the parameters, so keep in mind host to device. Well, you see that the parameters are initialized to 0. Well, here also we define another node. So in here, we need to use these functions. Make a heap extent to define the size, position, that will be, this is in case that we want to use some offset, but by default we will use 0. And then here I need to, for the point, use this function, heap give. Kevin, you say something?
No, I think you just disappeared for a minute.
Oh, okay. Maybe. Yeah, maybe it's mine. So I need to define all of these. Position will be by default 0, like the offset, and you see it's a bit more complicated here. We need to specify the pointer and also the size. And to add the memcopy node to the kernel, we need to use a heap graph at the memcopy node. Well, here, if we go to this link, we'll find more information. So once that we use the graph, because these tasks are they have some dependencies, so they are like handled in an asynchronous way. Before finishing the program, we need to synchronize. So we can do either heap stream synchronize using the default. When I say default stream is because if we don't specify streams, we will always use a default that I think is a 0 null. And also, if not, we can also use heap device synchronize. So either of these will make sure that the graph has finished. Because yeah, I forgot to mention that it's well, we assume that each node is done in a asynchronous way. It's not. That's the idea of having a graph. So here, this is the exercise that we'll try to do before lunch. So the idea is we have a template, a code template that the idea is to create the kernel, a node with the kernel, and nodes with the transfer, with the mem copies. And once that you do that, well, execute the exercise. Not sure if there are any questions. But yeah, if you have any questions, please let me know in the chat. I will try to answer them. Just to clarify, because I realized that I explained how to create a graph. Sorry, yeah, well, how to create a graph, how to create the nodes, but there is also an important point that I missed is how to create the dependencies. So we have the nodes, but what about the edges, the dependencies? The dependencies are when we add the node to the graph is where we need to specify the dependencies. So if we go here, when we have the kernel node, you see that here this third and fourth parameter are null and 0, because there is no, in this case, there are no dependencies. But if for some reason, for instance, for the main copy node, if we have a dependency, we use the pointer of the node that we have created before, that is the kernel node, and the number 1 that actually I think is The number of dependencies, so it's 1. I'm checking the, so here you can see the, so yeah, it's the number of dependencies and also the pointer of to the dependencies. Okay, so before going to launch, Kevin would like to explain some like a concept of graphs, and yeah, later we will have a launch from noon until 1 p.m. So, Kevin?
Yes, thanks, Juan. I just thought I'd say a little more about these graphs. So when I wrote the CUDA version of this material, I didn't put this in, but I'll tell you about it now. So this graph API business looks slightly painful and long-winded, but there is actually a shortcut available, which is referred to as the graph capture. So if you have a bit of code with mem copies or kernels or whatever you're interested in, you can basically top and tail this section of code by there is an API call. It's something like it will be something like hip stream graph capture begin, and then at the end you do hip stream graph capture end, and that sort of presses record at the start and records all the details of the calls or kernels and their arguments, and you can then sort of play that back, and that will execute a graph based on what you've recorded. So I have to say that when we first tried that with something moderately complex in CUDA, it just crashed. So I took the decision to explain graphs in the long-winded API fashion, because I feel on slightly safer ground with this API approach than the capture approach. But that capture approach does exist, and you may want to have a look at it as a shortcut. Okay, that's I think it's now time for lunch.
Yeah, thanks, Kevin. And yeah, also I forgot to mention that yeah, Kevin was the person who developed the material for the CUDA version, and some other people did the translation to HIP. Okay, so time for lunch. See you at 1 p.m.